Now we want to go over the sum of a geometric sequence. So we went over the sequence definition, right? So we go back real quickly here. So geometric sequence looks like this. And we want to look at the sum of those, adding them up. So let's look at this. Okay. Oh, oops, too far. Okay. So let A sub n be a geometric sequence. A1 the first term, R the common ratio, R non-zero, and not 1. We're going to use the notation just like arithmetic. S sub n is the sum of the first n terms of A sub n. So this is what it would look like. So 1, 2, 3, right, all the way to n. So it would be the sum. Right, here's your notation for sum. A1 r to the k minus 1. Right, so that actually equals this. This is the formula you have for that sum. Okay, it's assumed r is non-1 and non-zero. So here's the explanation of how you get that. Right, so S sub n is A1, R1, R1 squared, etc. Okay, then what you do is you multiply both sides of this by r. Okay, so you multiply by r. This is just basically the technique of how to do it. And then we subtract these two equations. Okay, so S sub n minus, so this equation minus this equation. By doing so, all of these terms in the middle will be canceled out. And you'll be left with, and I went one too far on that. This should be, not sure where I went. So this should be, I changed the font size, I was doing something else. It should be plus A1 r to the n. Oh no, I'm sorry, that was right. I had that backwards. Okay, let's just erase all this stuff. There we go. That was right, because this is the other term. So this is the last term if you multiply by r. So this is the original, right? Because you're just putting in terms here, so this goes to n, so n minus 1 is the last term, or the nth term. Okay, so then you subtract in all these terms here and here cancel. They're the same. So you get A sub 1 minus, because you're subtracting it, minus this term. Then you just factor out A1, factor out S sub n, like that, and then divide. Divide both sides. Let's see, that looks right. This is duplicated for some reason. So you divide both sides like that, and I'll just leave it, it's fine. Okay, so this is your formula that we just proved. Okay, so that's the same as the one above there. Okay, so that's the one you remember. That's the sum of the first n terms of the geometric sequence. So so here's an example. Find the sum of that. Let me get rid of this stuff. And if you listed them out, right, you just get, if n is 1, you get a half, and then you get a fourth, and you get an eighth, like that. So it's multiplying each term by 2. So 1/2 times a half is a fourth, 1/4 times a half is an eighth, etc. So that's the term. That's what you're adding up. So you want to find n terms of that sequence. So you're just going to substitute in a half right here and here and here. Everything else remains just n. You'll keep n as a variable. So we say S sub n is equal to a half times 1 minus a half raised to the n over 1 minus a half. And so the work really is in simplifying that sum. You've got all these halves running around. Okay, so let's do that. So you get a half, and then times 1 minus a half to the n. And then you could think of this as over a half. So those are gone. So a half divided by half is 1. And so you just then have 1 minus a half. So it's equal to 1 minus a half to the n. Okay, and we can use that to evaluate something. I didn't ask you initially, but let's just suppose I said find s sub 5. Then it's basically 1 minus a half to the 5th. And so that's be 1 minus, and then a half to the 5th is, you can just do 0.55 times if you wanted to, or just raise it to that power. So I'll do it again here. Let's get a decimal is fine for approximations. So 0.5, and then I'm going to raise that to the, 0.5 raised to the 5th power, 0.03125. And then subtract 1, and you get a positive 0.96875. So what's going to happen as you add more and more terms to the sequence? So if you look at, S10, S100, S1000, what's going to happen to this thing? Well, 1/2 to the n is going to get small, right? If you keep raising a half to a power, you keep multiplying a half. You could do that in your calculator. Just put in 0.5, and then basically you do 0.5 like that, and then you raise it, and you keep multiplying by the power. Just keep hitting the button, multiply, and you'll end up getting basically 0. So in other words, 1/2 to the n approaches 0 as n approaches infinity. We're going to use that concept to prove an infinite sum. So again, what happens to this sum as you approach infinity? Okay, so our conjecture here is that s sub infinity is equal to 1, because this little term at the end here starts to disappear the more terms you add. Which sounds strange, huh? But that's what happens when you simplify that function. So that brings us to an infinite sum definition. So here is another theorem. We'll just go on to this page. It's fine. Okay, so here's a theorem. It says if absolute value of r is less than 1, then the sum of a sub a1, first term, r to the k minus 1, as k goes from 1 approaching infinity, converges is what we say, meaning it's not infinite. Okay, so converges basically means it's not equal to infinity. Then its sum is, we say, s sub infinity is equal to a sub 1 over 1 minus r. Actually, a very much more simple formula. That's only true if r is less than 1, or the absolute value of r is less than 1. So that's the infinite sum. So this is the other one you need to know. This is the infinite sum. That didn't work. Of a geometric sequence. So infinite sum of a geometric sequence. Okay, so let's use it to basically prove. Well, first let me show you this. So if you take S, so here's the proof of this basically. So we're going to assume that absolute value of R is less than 1. Okay, then from previously we know S sub n, meaning the sum of the first n terms of geometric sequence, is A1 times 1 minus R to the n. That is all over 1 minus R. So you simplify that, and you get A1 minus A1R to the n over 1 minus R. Now divide each term by that, and you get A1 over 1 minus R minus A1R to the n over 1 minus R. So what happens then as n approaches infinity? So as n approaches infinity, what happens to R to the n? Well, if you're assuming that R is less than 1, you can show, or we're going to just basically understand that raising a fraction between -1 and 1 to infinity is going to go to 0. So this whole thing is going to approach 0. So that means this whole thing approaches 0 as you approach infinity. So what you're left with then is this form right here. So that whole term disappears, which is essentially what we got back here. Right? This was the term that approached infinity as you kept going. That's the same basic form that you end up getting there. Okay, so that's basically it. Let's use that to do the previous one. Okay, so next example. Oops, don't want to use red. Find the infinite sum which is 1/2, 1/4, 1/8. It's the same one we just did. So we know R is equal to 1/2, which is less than 1. So we may apply the infinite sum formula for geometric. Okay, so it's geometric. Okay, so S sub infinity is A1 over 1 minus R. So finish that. What's the first term? What is R? Substitute and simplify that. So you should get 1/2, 1 minus 1/2, 1/2 over 1/2 is equal to 1. So sure enough, it does go to 1. Okay, let's do one more example, and then we'll go on to the next section. All right, so this was an example, find the sum. So n is 4, and then you approach infinity. 18, and then 1/3 to the n minus 1. So the first term, so this is an infinite sum because you're approaching infinity like that. Oops. So what you want to do maybe is write out your terms of the sequence to figure out what that is. So it's 18, and then 1/3 raised to the, well, you're starting at 4, so this is 3. And then it's plus 18, 1/3 to the 4th, right, etc. and you want to see what that is going to equal. Well, the first term, this is a 1, this is a 2. You need to know the common ratio for your formula, which is right back here. So here it is. So you need to know the common ratio, which is R, and the first term. So the common ratio is what? What's that? That's got to be 1/3, right? So R is equal to 1/3, which is less than 1. And A1, if you simplify that, is 2/3. So this is 18 over 27, which reduces to 2/3. So A sub 1 is 2/3. So then S sub infinity is equal to the first term divided by 1 minus R. So the first term is 2/3. We just figured that out. Over 1 minus R, which is 1/3. So that's 2/3 over, and then 1/3 minus, or 1 minus 1/3 is 2/3. So you get 3 over 3 and subtract, so you get 2/3. And so look at that, you get another 1. So that sum also adds to 1. The closer, so the idea is, I mean, you're never going to get to infinity. So, but you could just keep adding terms of the sequence, and essentially you can get as close to 1 as you want, basically, the more you do it. I mean, you just make that assumption that you just keep going, and you will eventually get as close to 1 as you want, just by adding terms of that sequence. Okay, so that covers 8.3. We're going to go on to 8.5 next, and then 8.4 will be the last thing we cover.